This is Syzygy episode 36, Scopes on a Plane. And welcome back to another episode of the Syzygy podcast, the only Syzygy podcast that features Samuel L. Jackson. We're talking about scopes on a plane this time around, as well as the first molecule in the universe. Does that sound right? Sitting opposite me to explain what the heck we're talking about, Emily Brunston. Hi, Emily. How you doing?
Hello, hello.
So what are we talking about? Scopes on a plane, first molecules ever. What?
Well, let's come back to the story first of all.
Okay,
so the
I'm
story,
getting ahead of myself.
You are. You're getting very excited.
I am.
It's just because I told you that about the plane thing.
I know.
I should
It
have
is
left
very
that
exciting.
to last.
Very exciting. I mean, anything that involves Samuel Jackson, I think, is worth doing. So, that had to be the title from the very start. But what are we talking about?
So we are talking about a brand new discovery that came out just over a week ago, where we have finally, after a long, long time of searching, found the very first molecule that ever existed in the universe.
Right. Now, this... Okay, when you told me about this, and then I did a admittedly very small amount of reading about it, the first thing that jumped into my head... Okay, there were two things. The very first thing was... That's not the molecule that I thought it was going to be. So we can come back to that in a minute. I was expecting something else. A little bit like that black hole picture from a couple of weeks ago. I thought it was going to be the center of our galaxy. It was a completely different galaxy. Threw me for a loop. Anyway, this one has thrown me as well. But the other thing was, surely we would have seen this already. You know, if this was the first one, then why haven't we seen it before? So there's a lot to unpack here. Plus, there's also scopes on a plane, telescopes on a plane, and we need to get there. So who are we talking about? Where has this been published? Who are these people?
So this is a team who work with a group called SOFIA. So it's a Nature publication that came out. It's a lovely written article, actually. I really enjoyed reading it. It's sort of one of those, just you think, oh, the author of this has done a fantastic job.
It is nice when you come across those. I mean, scientific articles can be a little bit, shall we say, prosaic at times. You know, here's a bunch of stuff that we did, and here are the results, and there's a lot of maths, and here's some tables of data, and it's just a bit sort of, and if you're into it, then that's great. But sometimes you come across one which is, no, they've taken time and care and effort to actually write this thing, and it really works. This is one of those.
Yeah, and you get the sense from it. It's like, well, we found the first molecule in the universe. We're not really sure if it has much application beyond just kind of finding it. But it's really nice that we found it.
So they've really gone out of their way to get across that excitement and the sense of wonder at finding the first molecule, which is nice. It's nice to see that coming across in the prose. So, you know, literary critique aside, what have they found? What is this thing?
Okay, so we've found a molecule which is called helium hydride.
Helium hydride, okay.
Now,
not remembering my chemistry terribly well. That's got helium in it.
Yes.
And it's got hydride? What's the
hydrogen?
Well, yeah. And just hydrogen? That's it.
That's it.
Okay.
Yeah.
So the hydride bit is just one hydrogen stuck on.
Exactly. Yeah. So it's not something you sort of go into the chemistry cupboard at the back of the school lab and pick out and say, oh, I need some helium hydride to do my experiments today. It's not a very common thing.
Okay.
So
which presumably is why it hasn't been seen until now? Like, is this a difficult thing to make?
So it is a bit tricky to make, because what happens is you've got two elements. And let's think about helium, right? Helium's a noble gas.
Yeah. And that means, though I haven't done a lot of chemistry in a while, I've done enough to know that means that it doesn't react a lot.
No,
right?
it doesn't
it's
really.
Pretty standoffish. It does its own thing and doesn't like to react with other things very much.
So it's not a particularly exciting, I'm going to go out and nab all the different electrons from different molecules. It doesn't make molecules very easily. So you wouldn't expect it to be kind of the first and therefore the easiest thing to make in the universe.
No, I mean, I would have thought that there would have been plenty of other things that would have happened before helium starts getting involved in the chemistry, but apparently not.
Well, maybe we should walk through kind of a timeline of the universe.
Let's do that.
Yeah.
Because we haven't done one of those in a while.
No, I think, well, if you want to listen to a bit more detail about nuclear astrochemistry, if you like.
Which we all do.
Then episode 30 was when we looked at through the periodic table.
Oh, we did. That's right. Yes,
Remember
because
that?
it is International Year of the Periodic Table, and we went through that in depth. I seem to remember there were the metals and the non-metals.
The star poo. That was the headline from that episode.
Yeah, that's right. So go and listen to episode 30 and then come back. We'll wait for you. Okay, you're back. So, yeah, Helium?
Okay, so
That doesn't make any sense.
we go from Big Bang to having, hot, murky soup of nothingness, maybe some quarks or some very elementary particles. Eventually, we get some ions in the universe. So we get hydrogen and helium. Now, hydrogen's about 75%, helium's about 25%, and there's kind of a splattering of other stuff, but it's so little of it that it's almost not worth talking about.
Hang on, you talk about ions. Isn't a hydrogen ion just a proton? Isn't that what that is?
Yeah.
Yeah, okay. Yeah. But a helium ion could be a helium nucleus with 1 or 2 electrons around it, being a helium atom, 1 electron being a helium ion, or no electron still being a helium ion.
Yeah, so you've got 2 protons up to 2 neutrons in the helium nucleus, and up to to get to the atom, you need 2 electrons for helium, right?
But point is, highly energetic, and so the electrons haven't really clustered around to make neutral atoms yet.
Exactly.
Okay.
Yeah. So in a high energy, high temperature, this is important for the Big Bang environment, because remember that after the Big Bang itself, then we've got a cooling universe as it expands. So it starts off insanely hot and it gets cooler and cooler and cooler. And as we step down in temperature, different things are able to form. So we start off at 32,000 years after the Big Bang is when we start to go from helium, which is doubly ionized, so having no electrons at all, to helium having 1 electron.
Okay, yep. Singly ionized helium. Yeah.
Yeah. So from
After 32,000
chem
years.
speak,
Yep.
we go from He++ to He+.
Yeah.
Yeah. So it's just 1 ion. Now, then after another 132,000 years, 100,000 years from then, which is 132,000 years from the Big Bang, then the helium ion is able to capture its second electron.
Okay, so cosmologically speaking, we're cooling quickly. It's still a long time, but in comparison to the length of the universe, I guess not so much. So now we're finally down to helium.
Yep, neutral helium, but hydrogen is still ionized. So helium, it's part of its being a noble gas. It wants to become a neutral atom, so it does that much quicker than hydrogen does. Now, we've got this kind of gap then between 132,000 years after the Big Bang and 380,000 years after the Big Bang, because at that 380,000 years is when hydrogen becomes neutral.
Okay, so there's this long period where helium is cool, it's hanging around as an atom, but hydrogen still ionized. Hydrogen is still basically protons and then electrons flying around.
Yeah, so hydrogen's out there hunting down for some electrons to play with. And it turns out that the only ones that it can find are the helium's bound electrons. So becoming a molecule means that you're sharing an electron. So what you have is this neutral helium, and it's got these 2 electrons, and the hydrogen comes along and starts to share one of them.
Now, again, remembering back to my high school chemistry, and this was a long time ago, so forgive me, but I thought that kind of the point of helium was that it doesn't like sharing its electrons very much. I would have thought that other things would be much easier to do than hydrogen joining a chemical bond with helium, but apparently not.
Yeah, well, and this is also why it's very short-lived. So once hydrogen becomes neutral, then hydrogen really wants to become a hydrogen molecule, so 2 hydrogens together. And so that reaction takes preference over this helium hydride existing. So it's only really in this window of time that you get a huge amount of helium hydride. And we actually think that 500,000 years after the Big Bang, probably all the helium hydride's gone.
Right. Okay. So we've got a situation where we've got this fairly unique set of circumstances. You've got neutral helium. It's got all the electrons it needs. It's totally fine. You've got ionized hydrogen flying around going, just give me an electron. Just anything. Just give me something. And turns out that energetically, it kind of works for the helium and the hydrogen ion to stick together at that point. But once you're beyond that point, you're saying that when you've got hydrogen as an atom, proton with an electron going around the outside, when you've got those flying around, it's much easier for the hydrogen to get together with another hydrogen and make H2. And that's fine. Leave the helium out of it. Get out of here, you noble gas. We don't need you anymore. But just for that short period, turns out helium hydride? Helium hydride is a thing.
Yeah. And it's the first molecule that was ever formed in the universe.
And the reason why I got confused was because I kind of thought, but surely H2, hydrogen and hydrogen. There's loads of hydrogen around. Surely that's the one. But there isn't neutral hydrogen yet. There isn't hydrogen that can make H2, yet there's hydrogen ions, and that's the point. And just for this short period of time. Cool. Okay. Now, my next question, didn't you say that it was really short-lived? And didn't you say that it was only for a very short period of time after the Big Bang? In which case, how is it being seen now? How does that work?
That's really good. So this is a little bit of a English language, I think, inconsistency here. When we say the first molecule, I'm not talking about the actual molecule that was the very first one that was ever made in the universe that just happened to be spinning around near us.
Not sitting in a glass
in the
jar on
galaxy.
the universe's shelf somewhere going,
got a little-
first, this one.
Got a little flag on it that says, I'm number one.
So it's not that.
No.
So what is it?
No. In fact, what we have discovered is that we've been able to see helium hydride in the universe, which we've never, ever seen before.
Okay, so it's not... I mean, I had thought when I first saw the headline, I thought maybe this was one of those, we've seen the signature from the Big Bang and it's got helium, like, you know, how you can sort of, the what is it, the
Cosmic
microwave background is what I'm trying to say, is the leftover glow from that heat of the early universe. And I think we've got an entire other episode of the show to talk about that one. We'll park that one for now. But it's kind of a signature of the Big Bang. It's there, it's everywhere. And I thought this might have been sort of a kind of one of those subtle things of, okay, there's none left anymore, but we can see this signature of helium hydride. But no, you're saying, no, they've spied other helium hydride in the universe, in other places. This chemical, this compound, which would have been there in those early stages. We're seeing it in other places now as well.
Yeah. So this is modern helium hydride. It was formed relatively recently.
Okay, but we've seen loads of stuff in the universe. So I've got all these questions. Why is this one so hard to see? Like, why has it taken... Like, we can see black holes, Emily. Why couldn't we see this before now? What makes it so hard?
So it's an energy problem, really. So helium hydride, as with many, many chemicals, the way that we detect them is by the light that they give off when they're formed. So helium hydride gives off when the helium atom comes together with the hydrogen ion, a photon comes off. And that photon has a very specific wavelength. And it turns out that it's 149.1 micrometers.
Okay.
Now, that's part of the infrared part of the spectrum, right? So infrared astronomy is a huge area of astronomy. We cover all the spectrum, really. But we've been doing observations in the infrared for a very long time. But that's quite far into the infrared for us. It's actually a really difficult part of the spectrum to observe. We can't observe it from the ground.
Why is it so hard? Is it because it gets blocked by the atmosphere, or what's the deal there?
So our atmosphere contains heaps of water, and it's usually water that's the culprit here. So water molecules, water vapor in the atmosphere is very, very good at absorbing infrared light, right? I mean, think about your microwave, right? How a microwave works is you take microwaves, which are micron sort of size, same sort of size, and you get them to pump into your piece of food. All the water molecules in your food start to vibrate. That gives them energy that increases the temperature.
That's heat. Yeah. Okay. So all the water in the atmosphere is blocking any signal that we might want to see from this sort of far infrared part of the spectrum. And so it's pretty difficult to look up into the sky and see these particular photons that would be given off by helium and a hydrogen ion forming together to make helium hydride. And so it's really hard to see.
Really hard to see.
But we've seen it. Hurrah.
So you've got to get above the atmosphere.
Right.
Now, the usual way that astronomers do this is to poke a telescope out into space, right?
Yeah. We've got a few of those.
Yep. And we've even had many in the infrared. I mean, the most recent one was the Herschel Observatory. Mm-hmm. But it didn't observe at this particular frequency.
Right. Bit of an oversight, or just you can't do everything.
You can't do everything. Mm-hmm. And so...
helium hydride wasn't high on their list of priorities, it seems.
What we really needed was a kind of telescope that we could put into space, but then as technology evolved and we built new instruments, we could pull it down again, put on some new instruments and send it back up again.
I mean, that's not an easy thing to do with something like your Hubble Space Telescope. You know, that has been fixed over the years. I mean, didn't Didn't it sort of dock with the space shuttle at one point, or the space shuttle docked with it, came along, nabbed it, fixed a couple of things, and then put it back out there again. But it's not an easy thing to do, particularly as we don't have space shuttles anymore.
Yeah, and we've only done it a handful of times,
Yeah.
and Hubble's the only telescope we've been to
really?
to repair. So
Right.
it's
That
not,
one must really have been embarrassing then when it broke. It's like, look, it's going to cost a lot of money, but send the shuttle up, please. God, fix it.
Yeah, and we've got to the point where NASA have said no. If Hubble breaks now, it's
Right, that's it. You're done. Okay. So that's not really on the cards. You can't send one up into space. So
So if you need something that has to come up and down and up and down, well, we already have a piece of technology that does that.
Yeah, balloons.
It's an aeroplane.
Oh, planes. Sorry. Yeah. Although I guess you could have a telescope on a balloon.
We do have telescopes on balloons, so yeah.
I thought that was a big idea and it's already been done. Damn it.
Yeah,
Oh, well.
that's how we map the cosmic microwave background, for example.
Really?
Yeah.
Okay. There's another episode right on the board. We did that with a balloon?
With balloons.
That's awesome. Okay, but back to the planes. You're right. We do have a technology. It's pretty advanced now. So telescopes, what does that look like? It's not, I mean, I'm now imagining like your classic telescope dome on the back of a 747 opening up to the heavens. It's not like that, is it?
It kind of is.
Really?
It really kind of
You
is.
can't open a plane, Emily, can you?
You can. You definitely can.
Really?
So this is SOFIA. So SOFIA is an acronym for the Stratospheric Observatory for Infrared Astronomy, of course.
Mm-hmm.
And yeah, it's literally a 747. It's a 747. It's one of the special versions that Boeing made back in the 70s, whereby it was designed to do super long haul, super fast. So it's kind of a bit fatter than a typical 747, and it's quite a bit shorter. So it's kind of a stubby version.
Okay.
It's been a commercial. It wasn't a commercial aircraft for a number of years. It was a Pan Am airplane, and then American Airlines, I think, after that. So it's serviced, given its service to the commercial airline industry.
It's done its thing, and now it's flying with a telescope strapped to?
Inside it, and then there's just a big roller door on the side of the fuselage.
Seriously?
You open up the roller door, and then your telescope's
How
pointing
high
out.
does this go?
So it goes up to about 12, maybe 13 kilometres.
That's a long way.
It is. It's only a little bit above what commercial airlines do.
Wow. Yeah. Okay. So I keep coming back to, yeah, but there's a thing about opening doors on planes. Like we all know, we've all seen the films that if you open the door on the plane, everyone gets sucked out and dies. So
But
can't
that's
be
only
right.
if you're in a different pressure environment. So the way that this works is that there's, if you imagine your aeroplane, then towards the tail of the plane, there's a massive bulkhead, right?
Mm-hmm.
So the people are on one side of the bulkhead, the telescope's on the other side. And if you keep the side with the telescope in it at the same temperature, the same pressure as what it's going to be when your door's open, there's no sucking.
You're about to tell me that the very naive mental image that I have of people using this telescope is completely wrong, aren't you?
I'm sorry.
Yeah, it's not. I've just suddenly realized that I'm an absolute idiot. There's not people standing next to this thing looking through it, are there?
Well, there very rarely are.
No. I mean, I knew that. Really did know that. I can't escape from my
But they really are only a few meters away,
Yeah,
right, through this bulkhead.
But, I mean, that's the same when you're flying, right? You're only at most a meter away from the outside if you're next to the window. But that meter's pretty important. So,
Exactly.
you want to make sure that meter's there. And my mental image is wrong. Okay, so the telescope is open to the outside, but the people inside aren't. That makes sense. Thanks.
So it's a beautiful thing. And actually, I got to go visit SOFIA a few years ago. Yeah.
Visit as in fly with?
Well, no, I haven't been up in it, but I got to go in it when it was on the ground.
Cool. Where was that?
So this was in Christchurch.
Yeah.
So SOFIA flies 6 months of the year out of the US and 6 months of the year out of Christchurch in New Zealand.
Is that because of the seasons? Why?
Yeah, because you want the cold air, so you want to follow winter.
Right.
So the poor aircraft engineers and pilots and so on have to just basically have endless winter.
Yeah, but they get to fly a flying telescope. So, that's compensation enough,
It's
I
very
think.
cool. It's
Yeah.
very cool.
Yeah,
So
yeah.
it goes up for about 12 hours. And during this time, it will fly anything around 8,000 kilometers
Wow.
in 12 hours. From when it flies from Christchurch, for example, it heads towards Antarctica to get some really nice, cold, crisp air. And it's able to basically have a very, very precise trajectory such that if it modifies by something like a degree every hour on its trajectory, then you start to be able to track an object in the sky.
Yeah, okay. So that raises an issue. I feel like this is an episode where I've got a lot of questions and probably a lot of misconceptions. But hey, what the hell? I thought naively that telescopes were the kind of thing where you really wanted to isolate them from stuff like, I don't know, vibrations and movement, and you want to keep them as still as possible, don't you? Generally, isn't
yes.
that the idea?
That is
so
definitely true.
Correct me if I'm wrong, but bolting one to a plane doesn't sound to me like optimal telescope conditions.
It's definitely challenging.
Okay, so talk me through that then.
Okay,
How does that work?
Well, there's lots of optical corrections that we can do with the telescope to basically undo all the vibrations that are happening. So the mirror keeps deforming, the secondary mirror keeps deforming to keep up with all those kinds of vibrations.
But not in real time, surely. Really?
Yes, yeah, in real time. As the plane is going along, then you're keeping everything smooth. It's not quite as perfect and smooth as an optical telescope. Remember, this is an infrared instrument, so you're playing with light that's a bit longer, which means you've got a bit more wriggle room.
It's a bit more forgiving.
Yeah.
Right.
So this is why this is one of the earliest systems of, originally it was one of the earliest systems of adaptive optics. But we've now got adaptive optics that are incredibly well advanced that we put on other ground-based telescopes that can cope with anything from small vibrations from people moving around in the telescope dome, and even mini earthquakes in some cases.
Wow. I mean, I hadn't realized that the adaptive optics was doing that. I mean, I knew about adaptive optics that is able to compensate for changes in the atmosphere. But I hadn't really thought through the fact that this is basically doing the same as your smartphone's camera when you're taking a video, and it's able to compensate for the fact that you're moving around and give you nice, smooth video.
Well, there's actually two. I'm sort of interchanging my terminology here, which is a bit naughty. So there's active optics and adaptive optics. So this is really a lot of adaptive optics as well, which adaptive means you're adapting to the environment. Active means you're taking information, measuring what's happening to, say, a standard star, a laser star, and then making those corrections. They're subtly different, but all in all, there's a huge amount of wonderful technology that goes into it. And then you can get beautiful infrared images of objects in the sky.
I find that so amazing that you can put a telescope in a plane and correct for all of the stuff that's happening to a telescope in a plane, and it works. That's extraordinary. Absolutely amazing.
Yeah, and it's one of those wonderful stories because no one seems to know about this.
No.
But we've been doing it for decades.
The unsung hero of flying telescopes. Anyway, so coming back to the actual story then, this thing was used to find the molecule.
Yeah, so we needed to build a new instrument to go and probe this frequency band. And the instrument was great. I mean, literally, it's called GREAT.
Oh, okay. Another fantastic astronomical acronym. GREAT.
The German receiver at tetrahertz frequency.
They're really workshopping these ones hard, aren't they? We haven't used that one before. Crowbar it in.
Yeah, SOFIA is a collaboration between NASA and the equivalent of NASA in Germany, which is the German Aeronautics Center, or DLR, I think it says.
You don't hear a lot about Germany and space, do you?
It's a huge industry, and the technologies behind these kind of things.
Yeah.
So, like all the instrumentation, the telescope, etc., and SOFIA is German designed, and much of it was built in Germany as well.
I guess what you do hear about is European space, and there's a lot of that. So,
yeah.
Okay.
Yeah. So they were able to build this new instrument because SOFIA goes up and down and up and down. It has about 100 flights every year. They were able to just whack it in when it was on the ground and then take it back up and see what they could see.
Excellent. And what they saw was the molecule.
Yeah. Now, where did they see it?
No, I've got nothing. I've got 0 for 10 so far on this episode. So I'm still reeling from the fact that I just got the whole astronomers on a plane thing so completely wrong. So I'm going to ask that one straight back to you. Where did they find it, Emily?
They found it in NGC 7027.
That was going to be my next.
Of course.
Yeah. Which is what?
It's
where?
a planetary nebula. Now, planetary nebula are rubbish names for objects in the sky.
Because they're not planetary.
Nothing to do with planets.
But, okay, this is testing my memory. They're called planetary nebula, because early observations, they looked a bit like maybe they'd sort of planetary systems. They kind of had this ring of that looked kind of like there might be planets involved.
Yeah, I mean, it comes back to nebula as well. I mean, nebula is a terrible word in astronomy as well. It just means smudgy thing, right? So NGC numbers can mean planetary nebula, which are things inside our galaxy. They can mean entire galaxies. So there's just no consistency.
So smudgy thing number 1643
Pretty
is
much.
that one. Yeah, okay.
So we named them before we knew what they were, basically. Anyway, so this one's planetary nebula, which means it's the remnants of a fairly low mass star. So when a lowish mass star, so something from basically anything smaller than the sun up to a few times the mass of the sun, will not explode in a giant supernova and have a beautiful kind of enormous ring of material.
It's not going to go out with a big bang. It goes
Something
out
like-
with
It goes out with a kind of a quiet poof.
just a bit of a whimper.
So during the later stages of its life, it starts to shed all this material out, and you get this material sort of shell that might have an interesting structure around the dying star. And then the very dying star in the center of it illuminates the rest of that material from the inside. So it's kind of they look a little bit similar, planetary nebula and supernova remnants, but the energy differences are quite extraordinary.
I'm imagining they're not nearly on the same scale either, that surely the explosive power of a supernova must send stuff out to much greater distances than this sort of wimpy, slowly sort of sloughing off of your outer skins as the lighter mass ones, or does it? They end up the same size.
Yeah, and the time that they stay and hang around in the sky is quite different too. So
Right.
a supernova remnant will stay around for thousands of years, whereas a planetary nebula probably only a few hundred years
Right.
before it kind of ekes its way into the blackness.
Okay,
So
so
this
it's in
one-
one of these fairly wimpy nebulae that
Yeah.
this has been seen.
And that's actually one of the wimpiest ones that we know about.
Oh, good, excellent.
So it's one of the smallest planetary nebula, but it's quite close. So it's one of the brightest ones.
Right.
as
Okay.
well.
I was about to ask: is that on purpose? Do you go looking in the wimpy ones because for some reason it'd be easy to see, or is it just that it's nearby?
Well, I think this one was chosen because we knew some more information about what was going on in this particular one. So this one's interesting because it seems like there's a lot of UV light coming from the center. From what's left in the middle is a white dwarf. Possibly that's because the white dwarf is kind of active and it's maybe accreting material or it's pumping out something. It's got some energy source that means it's
Something's
still
going on.
Yeah, pushing out a lot of energy. It's probably only 600 years old or so since the star kind of died. But something energetic is going on, which means that you get a bit more ultraviolet light into the planetary nebula than you would normally expect. And what that means is that you set up this region which looks a little bit like the early part of our universe,
Okay.
because you've got lots of hydrogen and helium, because stars just have lots.
It's just there.
Yep. And you've got a zone in which you're going to have the hydrogen, which has been ionized by this UV light, but the helium still being a merry helium atom. So if you've got those two just under the right temperatures, then you can put them together and get this helium hydride.
So going to this kind of region and actively looking for helium hydride, that was the whole point, is we reckon we're going to find it here because this seems about right. This seems to be a perfectly good chemical laboratory for what we're looking for.
Yeah, and we've been trying for ages.
Really? So this has been an
Ages.
active, like, we know it's out there. It's got to be out there somewhere, or at least we know it was there. Let's see if we can find it in the current era.
Yeah, so we made helium hydride in the lab all the way back in 1925. So we knew that the molecule could exist.
It's possible, and it's possible under the following conditions.
Yeah. And then from the 60s and 70s, we were like, maybe we can find them in planetary nebula because they've got the kind of right set of conditions. But although there have kind of been hints of detection from lots of different observatories, never really a full-blown, yep, that's it, nailed it, got it.
So you said this has been found in a planetary, what was it called again?
NGC 7027.
7027, rolls off the tongue. Do we have a name? Does it? Or is this one of the
Well,
unnamed ones?
Only informally and only by amateur astronomers. So if you get a big enough amateur telescope and try and go hunting for this thing, it's not easy. As I say, it's not a super big one. You need to have quite high magnification, something like 50 times magnification. But if you do that, you get a fuzzy blob, and the fuzzy blob looks a little bit like a gummy bear.
And that's what it's called?
It's called the Gummy Bear Nebula.
It's called the Gummy Bear. Of course it is.
But of course, you could just go to the Hubble image, which is just vastly beautiful, and look at the interesting structures that you get in there.
Check out the show notes; it's in there. I mean, it's always kind of fun to, to put a full stop on something that we, from the theories of the early universe, from the models of the early universe, we think this is going to be there, right? But it's not there now. It's all gone now. We created it in the laboratory. We should be able to find it out there in the universe. And finally, using a telescope on a freaking plane, we've actually seen this now. Full stop. But is there anything about this final, hurrah, we found this molecule that allows us to, do we understand more about planetary nebulae now? Or is it really just yep, done it, write the paper, let's move on?
I think it's really just one of these rare examples of, okay, we've got proof that it exists in the universe. Cool. And I think that's why the article's written in kind of that tone. It's sort of like...
It's almost like an epitaph to a research program.
Yeah, it's so unusual that research doesn't generate 1,000 million other questions that go behind it. But in this case, it sort of seems to be like, yeah, cool.
And we're done.
Yeah.
And coming to the end of this Flying Telescope-tastic edition of the Syzygy podcast, I had some of my questions answered today, and there's a bunch more spinning around in my head, and I looked a bit foolish, but to me, that's kind of the essence of this podcast, that I have foolish questions and Emily answers them with great amount of sort of encouragement and respect. So thank you, Emily, for that.
There's no such thing as foolish questions. To be honest, if you'd told me when I was, not an astronomer, I'm going to put a telescope on a plane and that's going to be a good idea, I would have looked at you a little bit strange.
Yeah, I don't know. I still feel a little bit like the thinking that there were people looking through the telescope while the plane's flying. It's just... There's no eyepiece on this one, is there?
No.
So I see. I should have seen that coming.
But there's no eyepiece on Hubble either. I hate to break it to you.
I know that. I just, I do know these things, but I'm a bit slow. Anyway, we've talked enough about that. We need to finish this one up. Look, if you want to get in touch with us, which plenty of people do, well, some people do, then you can do that in a whole bunch of ways. First of all, you can go and check out our website, syzygy.fm, where you can find all of the past episodes and all of the information about everything that we've talked about over the last 36 episodes. You can find them all there, syzygy.fm. But that's not the only place. We're on social media too, aren't we, Emily?
Yes, we are. We're on the Twitter.
We are.
So if you like your information in X characters or less, I can never remember which one Twitter is now.
240?
I think you're quite generous with Twitter now. So yeah.
You can have whole sentences and
we can squeeze
everything.
in some pretty good astronomy facts, I think, into that space. So if you are into the Twitterverse, then do check us out at Syzygy Pod, SYZYGY Pod.
That's right. And we are on the Instagrams as well, at Syzygy Pod. In fact, pretty much most places, if you're on the interwebs and you think, I wonder if Syzygy's there, just check out at Syzygy Pod and see if you can find us. And if
I need to learn what
there,
Instagram is. That's going to be my goal for the week.
Okay, that's your due by Friday. That's what you got to do. Okay, you got to be on the Instagrams. I'll show you how to do it. It's really easy. And look, I've got a request for you. We would love to reach as many people as we possibly can with all of this fabulous astronomy and astrophysics and cosmology stuff that we natter on about every week. So here's a job for you at home. Due by Friday. Leave us a review. Go to your podcast catcher of choice and find the way that you can leave a review. Apple Podcasts, whether it's Spotify, whether it's Google Podcasts, whatever it is, leave us a review, give us some stars, tell us what you think. We love the feedback, but it also helps us to rise up through the noise and stand out a bit as a signal amongst the noise so that people can find us and so that we can reach more of the world. That would be awesome.
We're still learning about the podcast universe, so we need your help.
We do. And if you've got questions, if you've got suggestions, you just want to say hi, get in touch. You can do that through the social medias, or you can do it through our contact page on our website. But otherwise, we'll be back again in, a week or so for another edition of the podcast. Any ideas for next time, Emily?
All of the universe.
All of the universe. I think we've come up with about another 6 ideas for podcasts just in this episode alone. So we'll pick one of them and we'll be back again in about a week's time. Until then, bye for now.
See you later. Bucket list goal to visit all of the observatories around the world. I've got at least the movable one.
Yeah. Well, one of the movable ones. You haven't been to space. You haven't visited Hubble.
No.
Sorry to bring you. I was about to say, bring you back down to Earth. That doesn't right.
We might have to park that one. One day Hubble will come back to Earth, but in a lot of pieces.
In a lot of pieces. You could maybe visit bits of it.
Yeah.
And telescopes in space.
Yeah.
Do we want to?
Scopes on a plane?
Scopes on a plane. Scopes on a plane. I like that. I think that's okay. Done. Scopes on a plane.
Can we just get these telescopes off this plane?
Astronomy as done by Samuel L. Jackson. And I would pay to see that.